So it has been quite a delight to be here this week, and being a person who really only sort of dabbles in machine learning, I'm feeling this giant imposter syndrome of giving a review talk at this meeting. But um, and it also is made especially challenging because there actually have not been very many applications of machine learning to JWST data. So some of this review is somewhat aspirational. Um, and I will, at some level, talk a lot about just what's going on with the observations and what results are coming out to people's appetite for what might be done. So first of all, is machine learning even needed for JWST? The data volume is not probably driving this. 57 gigabytes a day is the maximum that we can download from the telescope. That's 2 millirubins. And so, it's a good testing ground, but it's not, we're not driven that direction. And a lot of the inference, especially in the first images and spectra, really, traditional techniques of, regression with your fingernails and things like that suffice for some of the early results. But there is a lot of promise in machine learning, and I'm extremely excited about some of the things that I've been seeing this week. So fresh approaches to difficult inverse problems. So one of the really, I think expectedly, but nonetheless brilliant things that's coming out of JWST is spectroscopy of distant galaxies. That is really pretty phenomenal and not that hard to get. So you can get a low resolution spectrum of a galaxy with JWST in the same amount of time as it took you to get an image with C3 on HST. And so you can sort of go wholesale at least into low resolution spectroscopy. And then at this resolution, R of 1,000, if you have a strong emission line, it actually translates pretty well to the same sort of exposure times. So sort of 1 hour exposure times are, there's a heck of a lot of high redshift science that can be done with just a few hours of exposure time. So you get a spectrum like that. You've got these emission lines, you've got the continuum, you'd like to derive the metallicities, the ionization parameter, densities, maybe dust depletion, star formation, stellar mass, star formation histories, things about the escape fraction and the ionizing photons, maybe a black hole mass, sphere rotation, things like that. So there's a giant inverse problem if you want to convert spectra into physical parameters. And that's a place where I think there's already been some quite interesting advances on machine learning, and that could be turned right to interpreting JWST data. Another thing that machine learning is going to offer us and is offering us is fresh approaches to forward modeling. So we've got all these physical parameters on one side, and we've got images and spectra on the other side. And we would, in some sense, like to forward model without essentially dimming the lights in Europe. And so we need convenient, reliable techniques that are quick, that allow us to explore large amounts of parameter space efficiently. And so there's lots of fresh approaches out there, and it'll be exciting to see that. And then the title of this conference is Data-Driven Discovery. And when I think of data-driven discovery, I think of things that you can't do an inverse problem, you can't do forward modeling because you didn't know it was what you were seeing. So one nice example I like is the sequencer from Brice Menard and company that just looks at ways of organizing data that might pick out patterns that are there that you didn't know were there. So on the bottom, that's an image, a scrambled image of Einstein that only comes out when you sequence things. And there's a clever way for it to try to sequence things and look at what might be pulling out information. In the middle row is, I think these are quasar spectra aligned with redshift. And so finding patterns, I think, will be interesting. I actually asked the new font of all knowledge, ChatGPT, to tell me what discoveries had been made with data-driven discovery in astronomy. And I asked it 2 different times, and it came up with, and then now of course it stopped looking at the internet in 2021. But the two it came up with, one was exoplanets, and not being in that field, I'm not sure if that's data-driven discovery or if that really was prior based, let's go search for patterns that we expect to be there. And the second was galaxy classification and things like that, which I don't yet see as discoveries. I see as, yeah. So I'm not sure. I would love to know if somebody has an example of a purely data-driven discovery that in some sense came out of machine learning. I mean, there's obviously discoveries that come out of looking at data, you know, so on, but one that came out of an application of a machine learning technique. I think we have yet to have a big, brilliant example of that. And then I do think it's interesting. Machine learning, of course, Bayesian thought about priors. Bayesian techniques thought a lot about priors, but I think machine learning is really incorporating that from the start. Interesting ways of incorporating priors into objective functions and things of that sort. This is my favorite prior, you know, where's the kaboom with, you know, back in the 1960s where we thought galaxy formation, or 1970s, 80s, where we thought galaxy formation was one big thing. So outline of the rest of the talk. I want to give some highlights from the early JWST observations that have nothing to do with machine learning, but are just, you know, sort of things we're finding. Then review some of the applications of machine learning to HST and JWST, mostly in the field of looking at high redshift galaxies. And then talk a little bit about the outlook things, my wish list maybe of things that we could do with machine learning with JWST. It would be wonderful in the discussion to think about things like where we could be most incisive. And then I'll talk a little bit about the Roman mission. So let's start at low redshift. This was one of my favorite tweets from the early JWST. So Gabe Brammer has been essentially pulling in the archive as it comes down and processing it. And he just tweeted this one out. Unfortunately, probably scooping the people who were actually taking the observations, but nonetheless, it's a gorgeous image of a nearby galaxy in the PAH features in the mid-infrared. And it's really intriguing just looking at that, especially if you looked at hydro simulations that show qualitatively similar patterns. So this is just a blow up. This is that galaxy in from the ground in the optical. This is HST. I would say you can, if you really squint at it, you can see that pattern in the dust. If you overlay the JWST and blink back and forth, you pretty much see the same patterns in emission that you see in absorption, sort of. And so there's a huge interesting topology there that, as I say, looks qualitatively like simulation. So here's a same galaxy simulated with 5 different subgrid recipes, trading off supernovae, protostellar feedback, varying star formation triggers, and you get a different topology of the interstellar medium for that. So there's interesting constraints, I think, on the kinds of physics that are going into building our distant galaxies and making them look realistic and so on and so forth. The analysis of that image so far, several other images taken in the same program, they've done a genus measure, which is a measure of sort of the topology of the connectedness of the PAH features, basically, where it goes smoothly from being a high number, the genus statistic, if you have a sort of a meatball-like topology, and being a low number if you have a Swiss cheese topology. And they're looking at how the topology changes as you go down in surface gas density. And what JWST is providing is high resolution at low surface densities, which is not something that's come out of radio observations of molecular clouds, for example. So it's interesting new constraints. They've compared to a couple of simulations. One of the simulations has a lot of physics in it, and it really is one realization. but came out really quite on what the behavior of the genus statistics that they're seeing. Um, that's, of course, taking that rich topology and compressing it into one number. I'm sure there's all sorts of things one could do with machine learning to either create multiple features or use the images themselves, go beyond simple summary statistics to really analyze the information, extract the information that's in there. And then on the other side, exploring, we've heard about ways to accelerate simulations by building sort of emulators, deep learning emulators and things like that. And that probably would be of use for exploring the parameter space. So then moving to more distant galaxies, this is one of the early release images. This is the Hubble image of this cluster SMACS 0723. This is the early release image, absolutely gorgeous. You can stare at this for hours. Obviously, this one is a lensed cluster, but there's a lot of galaxies in there that have low magnifications, a few that have high magnifications, and there have been quite a lot of interesting papers to come out of just that one image and a few spectra that were taken at the same time. Example spectra from those first few spectra, you can see galaxies from redshift 5 to 8, optical emission lines popping up, and just easy to start to do things with them. So motivations that have driven some of the distant galaxy surveys, we'd like to know the energetics of reionization. Do galaxies actually produce enough photons? If so, which ones? Feedback and chemistry. What's regulating star formation? What governs galaxy structure? Look for the seeds of massive black holes. See if there are enough of them. Do we have a problem there or not? And then test, in principle, perhaps test dark matter, so the masses of redshifts of early galaxies. If you can convince yourself you believe the baryonic physics, do give you constraints on dark matter. So I'll sort of walk through some of the high redshift discoveries that are coming out. Here's an example that just shows sort of the grasp of JWST. So this is a galaxy that was identified with HST. So these are the HST images out to the near infrared, and then the Spitzer images. And these are lined up at the same wavelengths as the JWST images down here. And you can see that JWST just comes booming in. These are 45-minute to an hour and a half exposures. The uncertainties on the photometric redshifts go way down. And in some level, just confirming the candidates purely with photometry has been quite easy. So redshift 9 which was very difficult and uncertain with HST, is now very easy and very certain with JWST, with one caveat, which I'll get to. With just 35 square arc minutes of images in the Sears program, there are a bunch of candidates now out to redshifts of perhaps 16. And then there are more from other surveys that are going to similar depths, and there are starting to be some deeper surveys. One of the things that's sort of fortuitous, and I had not thought about it all that much before we started getting these surveys, is the observing strategy sort of pushes you into taking 6 filters as being like the default, because you're taking, you get 2 at a time. And if you really want to span the redshift range, 6 is sort of better than 4 and not that much more expensive in some ways. And so whereas with Hubble, it was sort of always a stretch to get more than 3 filters into your observing program. Now 6 becomes the standard, and there's a lot more information in 6 filters. And so just that alone is making these early data sets richer than I had anticipated. so that you can start to make luminosity functions even from these tiny surveys. Initial impression is that luminosity function's not evolving that much as you go beyond a redshift of 8 to, sort of summing up all the higher redshifts. So redshift 9 is dominating this plot, but it just sort of overlays the lower redshift luminosity functions. Another way to look at that is just look at the cumulative numbers as you go out in redshift. So that's just taking the same thing, galaxies, and lining them up. And this then it gives you sort of a visceral comparison to what you might have expected from a whole bunch of predictions that were out. Some of them are physical models, some of them are reconstructions, some of them are just smooth extrapolations. All of them match, and I can't remember if it's at redshift of 7 or I think it's more like redshift 5 to 7-ish. They tend to match. And then by the you get to the beginning of this plot, they're already diverging, but they're diverging a lot when you get out to redshifts of order 13 or so. So this is where the sort of statements are coming, that it's surprising that we're finding even a few galaxies out at redshifts 12, 13, even out to 16, because we've only surveyed small areas, and these things are somewhat brighter and somewhat more common than we might have expected, and that's potentially quite interesting. This is just another look at that. This is the UV luminosity density, just looking at what the evolution was thought to be from some surveys on HST and what maybe now it looks like is more likely. And there are these exciting individual candidates at high redshift. So this one, I think, may be the current highest redshift one, the 16.4. It is quite convincing photometric candidate. It's one that was supposed to get spectroscopic confirmation in December, and the observations failed, and I think are happening this week. So we may get spectroscopic confirmation of this one. There are some galaxies that if you just had photometric redshifts and no other information, you would say are at higher redshift. At least there's one galaxy. But it has a radio detection, and so that one we're almost certain isn't. So there is a worry that there could be interlopers in these super high redshift examples. So the spectroscopic confirmation is absolutely essential, but it's not. It's a little bit challenging, but it's not actually pushing the limits of what you can do with JWST. At lower redshift, the confirmations are coming in. So the Sears project got spectroscopy back in December, starting to go through candidates that were targeted there. Among things that were about redshift of 9, 7 out of the 8 had clear lines. The redshift 10 to 13, there were a few candidates targeted. One of them has an ambiguous redshift because it's only one line, and there were no lines seen for the other two, which is actually sort of consistent with them being at high redshift because the lines that you might see shift out of the bandpass. The thing that's potentially interesting is that the redshifts, the spectroscopic redshifts, are coming in a bit lower than the photometric redshifts. So it seems like, at least for the code that's being used by the Sears team, but I think this may be more general, there's some bias in the photometric redshifts when you get above a redshift of 9 that the PHOTZs may be a little high. They're probably still high redshift galaxies, just maybe not quite as high as the photometric redshifts are pushing them. So that may say something interesting about the templates that are being used in those photometric redshift codes, maybe how they're modeling the Lyman alpha break. But we haven't gotten into quite understanding what that bias is. There are spectroscopic confirmations at higher redshift. These are with the prism with much longer exposures, 9 to 27 hour near spec exposures. And you can see the Lyman break just very clearly in these spectra. And they're quite convincing, even though you don't have individual emission lines. From those spectra, it's possible to make some derivation of physical parameters probably at a level that's somewhat better than the photometry. Certainly having a redshift and trusting it lets you fix things, even if you're going to use the photometry. So you can get constraints on the stellar masses and the star formation rate and the stellar ages. And they don't look crazy. From those emission line spectra that I showed earlier, you can start to see trends of trying to derive star formation rates. I think in this case, it's using the redshifts but then using the photometry to estimate the star formation rates, and then using the spectra to estimate the ionizing photon production efficiency. And it's early days on both of these plots, but these things are going to fill in very quickly. And this is the kind of thing you just simply, didn't have any data to do at these redshifts before, to compare to models at these redshifts. Chemical abundances. So in the very early spectra from that SMACS cluster observation, people started to do very quick and dirty analysis of the metallicity distributions and the trends of, say, mass metallicity trends. That's without even a calibration of the spectrograph at that point. There's been a lot of progress since then. There's a very impressive paper by Nakajima et al. That collected spectra from public surveys. So there are 111 galaxies on this plot from redshifts of 4 to 10. They went and did their own calibration, flux calibration at some level of near spec. And 9 of those galaxies had a direct method metallicities using the weak lines. They don't see much evolution over the redshift range 4 to 8. By the time you get to 4, you're already lower metallicity at fixed mass than you were at redshift of 2.5, 3. There may be some trend to lower metallicities as you go out to redshifts beyond 8. Early days again on this, but this is amazing with just a few months of data. So that's the kind of thing that you can really hope to get at the feedback physics in models with, because that drives the mass metallicity ratio among other things. And if you have both that and mass functions, you just have a whole lot more leverage. It's not way out of the ballpark of what models are predicting. If the models are predicting their scatter, then in some sense the scatter's much more out of the ballpark than the trend. But there may be observational issues on the scatter too. So this will refine itself. It'll be very interesting to see what this plot looks like a year from now, because calibrations will increase, improve, we'll get better samples, better ways to analyze, so on. There are also galaxies at high mass turning up at high redshift. These are, they could be quite surprising and quite constraining if you end up trusting the masses, even if their redshifts are not, out at 16, but, down at redshift of 4 and 5. So Eva Lebey, in some of the early observations, looked for double break galaxies where you had both the Balmer break and the Lyman break. Found 6 galaxies with masses probably above 10 to the 10 in the 31st square arc minutes that had been observed at that point. I think there's some debate about how trustworthy the masses are. And so this, and that of course it becomes key when you're going to use these galaxies. But there's probably much, yeah. Yeah, so at the, yeah. I looked for it last night and I did not see an update. And I didn't see somebody referencing and debunking that paper. So there might be something, going around Slack channels, but I haven't seen it more formally than that. things get a lot less ambiguous when you have a spectrum. So here is an absolutely gorgeous spectrum of a redshift 4.6 galaxy that had been previously identified and followed up by Adam Karnal. There you see a sort of classic post-starburst spectrum at high signal to noise. You actually see a broad line around probably H alpha, H beta. Yeah, I remember. And anyway, the constraints that you get on the star formation history are very tight. It's a galaxy that forms stars probably starting around just 7.5 or something, and then stopped forming quite quickly. If you then plot Ivo Lebes's galaxies on top of its star formation history, they sort of fall right on top of it, which is sort of interesting. But anyway, this is once again stuff that's going to be pouring in over the next year or two. Some of the spectra that have been gathered, these spectra were all gathered sort of just in the last couple of months. So Tang et al. Have stacked, well, they looked at 16 galaxies from redshift 7 to 9. In their paper, they stack them for this gorgeous sort of co-added spectrum where you can see a lot of the expected features. Stacks that I've seen so far, it's the helium-2, which you might expect from very early populations, is not coming booming through in stacks of things around redshift of 9 so far. So we may have to go out to higher redshift or down the luminosity function or something to be able to find things that are low enough in metallicity that the helium-2 1640 line is super strong. The other thing that's quite interesting, especially in this particular field, is there are clusters of Lyman alpha emitters. And so once you have a rest wavelength from these gorgeous lines, if you have Lyman alpha, you can look at velocity shifts and velocity profile of the Lyman alpha relative to the rest wavelength and start to get some information on the topology of any reionization bubble. Because the Lyman alpha will be affected by where the galaxies are in that bubble. So that gives you some constraints. They talk about that in the paper, but they don't actually analyze the bubble in detail. And I think there's people trying to look quite closely at this particular bubble and see if you can do things to say anything about the bubble geometry. So the ongoing survey, so there's a lot of imaging surveys that are getting time in cycle 1. And so we have everything from Cosmos Web, which is a wide, shallow survey, to NG Deep, it's now called, which is and the JADES survey, which has a deep component. Whoops. And the WDEEP observations, I think, are happening this week, maybe even today, starting. And so there will be spectroscopy certainly within months or so of probably more than 500 galaxies out at these redshifts, very high redshifts. There's also slitless spectroscopy coming in of thousands of galaxies. It's harder to analyze and slower to, in some sense, get out results there, but there's a fair amount that's been gathered so far. So now I want to turn to machine learning applications and just give a quick review of some of the things. There's really been only a few papers on machine learning applications with JWST. There's a interesting tool called Morpheus that was trained and applied on candles prior to JWST. So this comes from Howson and Robertson. And it's a convolutional neural network in boxes that slide across the image. And so it actually tackles detection, deblending, and classification all at once, and gives you, it can give you a segmentation map and tell you what's the best classification for your galaxy, but it can also tell you what they're doing in this far right image is they can tell you sort of pixel by pixel which classification is dominant and which is where it's uncertain. So you can sort of see how things play out if you have a well-resolved galaxy. I don't think we've quite figured out Yeah, I certainly haven't figured out how you would use that information. But it's very interesting information to have. Um, so that was applied to JWST images, I think from the JADES observations. And the quick and dirty thing, low-hanging fruit at some level, is look for high redshift disks, because a lot of the discussion that's going on the internet and so on is it seems like there are a lot of these high redshift disks. And so Morpheus classifications can just pull them out. They do Sersic fitting to these. They do look like disks if you do profile fitting. They look like disks visually, but caution, they don't look like spiral arms, flat disks with spiral arms. They look like galaxies with a sort of a Sersic profile that in many cases are more edge on. And in fact, when you start to look at statistics, and this has been done back in the HST days, the statistics of the flattening are not consistent with being drawn from disks viewed at a range of angles. So there may be some prolate or triaxial things coming into these samples, and I think we need to be cautious in interpreting whether there's high redshift disk formation or whether it's something a little more complicated than that. This is not yet a machine learning thing. This is a sort of a calibration sample of normal galaxies, but this is the kind of thing that is incredibly powerful, is taking simulations, numerical simulations, in this case from TNG's 50, snapshots at redshift 3 to 6, and making a very faithful NIRCam simulation. In fact, way more faithful than I would have done, of actually feeding it through the pre-proposal thing, through the individual ramps and dithering and putting in individual stars to align the images so that you have any misregistrations. You're doing everything the way you would actually do it with the images. And then measure, in this case, measure the half-light radius from standard profile fitting and compare that to the half mass radii that you have in the simulations. And it's I would say not particularly surprising that the match isn't perfect. And it's the kind of thing you could hope to use to calibrate any offsets, or to train a machine learning algorithm to analyze the images in ways other than the traditional way of measuring RE. So it's a gorgeous training set, and needs to be much bigger, of course, to do things right with lots of samples for training. Probably needs ideally simulations with different physics in them. But this is the kind of thing that will be very powerful. This kind of simulation, but a different set of simulations, were used to try to calibrate merger rate estimates. So populating NIRCam Sears images with images selected from Illustris TNG 100, and put down at the sub-ALOs that were in a semi-analytic model. So it's sort of a hybrid method of making a realistic looking image, and then using standard morphological parameters and standard cataloging to measure the features that people typically use to identify mergers, and then train a random forest to find mergers based on that feature space. The results, I would say, are not, to me, particularly surprising. That it's really hard with those standard morphology measures to pick out mergers, and the success rate's about 60%. And the false alarm rate's reasonably high as well. And so, but that doesn't say that you couldn't do better if you had a much bigger training set and you pulled more information out of those images than just the standard features. But I would say it's still quite hard, and this shows it's going to continue to be hard without a lot more effort. And then there's been some effort to extract parameters from spectral energy distributions, and I think Kartik will talk about some of that in his tutorial this afternoon. So there's a work with the Cosmos HST data to look at a self-organizing map way to estimate redshift and star formation and stellar mass and things, beyond just photometric redshifts, using the self-organizing map. It works reasonably well with the limitations that sort of self-organizing maps have. I think that by and large, if you have another data set that's identical, they're great. You can just apply it. It's the quickest thing you could possibly do. But if your data set's different, it's hard to know how to generalize it. And but it does really well, actually. So these are star formation rates, um, and yeah, star formation rates in both cases from the self-organizing map compared to star formation rates estimated from things that had nothing to do with the SED. So either from the H alpha or from the UV plus IR technique. Chartup and company have looked at, and this is the kind of thing that could be quite useful. It tried to come up with a formal way to look at the importance of different wavelengths, different filters at some level, in extracting information about stellar population as a function of redshift. And they look at the mutual information as a way to assess that. They use an UMAP to visualize things, and then they try to predict fluxes in missing bands, and they do quite well at predicting those fluxes. I think this kind of thing could be very useful for survey design, where you have limited amount of time and you want to figure out, do I really need to observe with all these filters? Can I get away with fewer filters or lower signal to noise or whatever? Hamadi et al. have come up with a way to deblend images using a GAN trained on candles, and then they're using it to deblend hyper-supreme-cam data, but also to deblend even HST data. So they're basically doing sort of a GAN-guided deconvolution, and then using that to find peaks, and then you can either do traditional photometry in those peaks, or you can do other things with your somewhat improved resolution. They get significant improvements in the photometry of this hyper-supreme-cam data when they start with the GAN deblended objects. So it's quite promising, especially in the application of trying to use improve the ground-based deblending. But even for JWST, deblending is a serious issue, and these kinds of techniques could be informative if we can sort of understand what systematics they imprint on what you're trying to infer. Finally, on the application so far, and this is one that's somewhat old, 2016 and 19, was an attempt to use machine learning to use essentially all the fluxes in simulated JWST spectra, every pixel, to estimate the escape fraction. So instead of doing features, you just treat every pixel, every wavelength as a feature. Do a lasso regression on that. And if you trust the spectral models that go into predicting the F escape, it does quite a good job of extracting F escape back out of the information in those spectra without doing any feature identification. So they're encouraging even for like 1 hour long spectra. I think there's a big leap of faith that the models that you could trust, that inversion, but nonetheless, it's a technique that's readily applicable, and you could probably do tests to see whether you actually believe your reconstruction. So this is a short wish list of just things that where machine learning, I think, could come in, probably have an impact. This one would be an impact that would be almost immediate. There are data reduction issues that are still plaguing and making things hard. One is there's a drifting bias level on basically all the HST instruments that gives you stripes across the image. And the frequency power spectrum of that drift is a 1/f power spectrum. And so the ways people have removed this so far have been fairly crude, as just to measure a mean in every line of the image and subtract that mean, or measure a slope or whatever. I think you could maybe take a Gaussian process approach, or some sort of approach where you're actually modeling the covariance of the signal there based on dark images or places where you could actually model that. And you could probably do a lot better job of removing these stripes and a sort of more formally correct job that doesn't require, that doesn't make you worried you're doing something bad to your data. Another issue is these cosmic rays that cause big cosmic ray hits. The cosmic ray here in the center is rejected, but there's sort of a spray of charge that isn't getting rejected. Those are appearing around the images, and so far the attempts to mask them are not perfect. They've gotten a lot better, but once again, you could probably train a network to find these things based on image morphology and actually know how to mask them or mitigate them in one way or another. And then background subtractance, the other thing, there's scattered light, there's I think other forms, well, by and large it's scattered light. And of course that's imprinted on your galaxies, and you have to make decisions on what's foreground and background, and that's the kind of thing that you can train machine learning to do, and probably do better than we're doing. Well characterized. So then, yeah, more toward data analysis and interpretation. So I think machine learning based source detection, deblending, photometry, and structural parameters. I think the challenge there isn't right now. Probably we could come up with techniques, and there have been some techniques out there, but to get people to trust them, to actually use them, is going to take a fair amount more effort of just doing things with simulations and doing things compared to traditional techniques and so on and so forth. And then you could hope, and this is my big hope, that you can skip a lot of the intermediate steps and not use the traditional features that we're using, but get, for example, mass distributions from light distributions, get merger parameters from the images, halo properties from the images, or infer them somehow, and do unsupervised classifications, the kinds of things where I think machine learning is really offering the biggest promise. The last few minutes, I want to talk about the Roman Space Telescope. So launches in 2026. It's basically Hubble at some level, the near infrared Hubble with 100 times or more the survey efficiency, aimed at a bunch of core science areas, dark energy being one of them, but understanding galaxy evolution is high on the list of things. Notionally, it'll have a 2,000 square degree survey. That's very notional. That's not set in stone. And it will have imaging and slitless spectroscopy. So for galaxy evolution, you could do clustering, gravitational lensing statistics versus all sorts of galaxy properties. The three things I want to bring up, and I think they're relevant to this community, there are huge near-term opportunities to get involved and help influence things. One is the observing strategy. So the observing strategy, there is a straw man observing strategy that is to be refined, and the refinement is starting now. I think we should seriously consider how to use machine learning to optimize the observing strategy, especially for the big surveys, depth versus area versus wavelength, or cadence, and when you're doing the time domain surveys, figuring out what's the best joint strategies with Rubin and Euclid in the mix. And so one should be putting forward ideas for complementary surveys as well. As I say, this is starting now, so there's a call out there for 1 to 2 paragraph science pitches. So very low barrier to thinking about this and just putting in some ideas, and no idea is bad. And those are due on the 17th of this month. That will be followed up with white papers with a much more technical, in deeper dive into trade space. But the call there, if you want to go to that website, is out on the web. Another big thing is there is funding for preparatory work. Those proposals are due on March 21st. The letters of intent were due a couple weeks ago, but it doesn't matter. You don't have to put a letter of intent in. There are wide field science proposals, which I would say are sort of more traditional science preparatory proposals. They're 1 to 2 years, moderate sized grants. And then there are program infrastructure proposals, which are 5 to 10 year. They're initially 5 renewable, that are really supposed to deliver, be sustained programs that will deliver things that are essential for the surveys. So that if you don't know about that, go to that site. And finally, making the data set useful. So post-processing, data analysis services, things like that. There is a software working group that existed, has been in hiatus while the science investigation teams reformulated. That is starting back up again this month. There is a lot of key decisions on data processing that have yet to be made and really will benefit from community input. There's also, there are a lot of pixels in that data. It's going to reside in the cloud, and there will be a science platform with high bandwidth to all the pixels. So computing near the pixels, that I've been deeply involved in specifying that platform. So far, machine learning applications have not really figured into the thinking of what's needed there. And we clearly need to think about how to provision that in a way that the community will use it, or if the community doesn't want to use it, we need to know that for sure. So sign up for that working group if you're at all interested. We'd love to have input. And that is all I wanted to say.
From a little bit into the question time, but that's okay because we don't bring more learning for today. But
seat mic or handheld for the people on Zoom.
Hey, Harry, thank you for the talk. I was wondering for Roman, do you know what the policy for ESA-based countries to contribute?
So the data are public instantly, or as close to instantly worldwide as they are in the US. There is very small formal involvement of ESA in the mission. So the bigger challenge might be how you get the funding agencies to give you funding to work on Roman when ESA is not a formal partner. But otherwise, the data are available, and collaborating with the US we're the platform, for example, we're planning to make available to regardless of nationality. So far, it looks like it will be easy to use Roman data no matter where you're from.
Now, ESA has a little bit of a contribution that with some antennas and a little bit of other things,
yeah.
and in return, there's some expectation that ESA will have some contribution to the working groups. But I think the calls are still to be negotiated and done, and so it will happen in the future, especially because in the US, the process is also happening at the same time.
Yeah.
We've talked a little bit this week, and you mentioned it again today, that there would be work to do to get the wider community to trust these machine learning techniques. And I was wondering if you could elaborate on maybe what you think some things that we could be doing to get a wider trust in them with this new data would be.
Yeah, so I think there's sort of two approaches. One is the simulation-based approach where you say, okay, trust my simulation, get everybody to believe you've got a somewhat representative, faithful simulation. And then you can prove things on simulation. But to me, that's like going to convince most people. There are some people who will not be convinced until they see that the traditional techniques give you some, that when you apply it in the regime when traditional techniques work, so when you use Gini M20 or whatever else you use for mergers, and you use this other technique, that you get at least as good. Now, to me, it's like, if you only do as that well, why are we doing it? So we really have to start being able to do better than that. But you will have to convince people that it's not doing harm. Right? So.
Other questions? Yeah, Mike.
Is this right? For these science pitches for the wide field survey, are there a set of requirements that already exist, and it's just about how to achieve them? Or are those like how to set, like what the requirements should be?
Yeah. So the science requirements for Roman are set, and they're not planning to change them, and they are informed by the cosmological science goals and exoplanet science goals and things of that sort. But so they will inform the survey strategy, but they don't presuppose any survey strategy. They just say things like, how precisely there's a very high level of how well you want to constrain cosmological parameters. And then there's a flow down to what that means to some kinds of measurements. But there's not a flow down that says we need to do 2000 square degrees in these many bands or whatever. That is very open.
Okay. So what you do need that whatever comes out of this has to flow up to satisfy some set of things.
So there is a thought that there will be a sort of a refinement of figures of merit as part of the process, probably maybe even after the white papers come in, to figure out, okay, how are you going to do this multi-objective optimization in some semi-quantitative way? So this is the kind of thing that Ruben struggled with, making figures of merit that are actually useful, that you compare apples to apples to on it. But it's a useful exercise, and I think we'll probably try to do something vaguely along those lines. I think the schedule is a little more compressed for Roman than it was for Ruben, so we probably don't have as much. We hope, we hope. So we may not have quite the luxury of time to do things in the level of detail.
Thanks.
Yeah.
Any other questions? So far, no questions online. No? Okay, let's thank Harry again.